the seminar in Tashkent, operator algebras and application, and its joint session with European Non-Associative Algebra Seminar, because our speaker, Professor Dotsenko, is now in Tashkent in our Institute of Mathematics. That's why we decided to organize this joint session. So today, as I mentioned, our speaker is Vladimir Dotsenko from the University of Strasbourg, France, and the title of his talk is Operads, Filtrations, and Quantizations. Please, Vladimir, you are welcome.
All right. Thank you very much for the invitation. I'm now spending several weeks in Tashkent by kind invitation of Professor Ashmatov. It's really wonderful to be here. It's my first time in Tashkent. I'm enjoying my stay here very much. So yes, I will talk about some algebraic viewpoint on the notion of quantization. So somehow, of course, for most people who think about quantization in various forms, geometric quantization, deformation quantization, and so on, the motivation comes from mathematical physics. So somehow there is the story of classical mechanics, which is based on, if you want, on the Hamiltonian formalism or on Poisson geometry, and then somehow quantum mechanics, where the protagonists are operators on, let's say, Hilbert space, which form themselves an associative algebra, and quantization somehow describes the passage from one story to another. So somehow there are two aspects of what I'm going to talk today. So first of all, I will explain some, so I will talk about some way to think about all this algebraically, if we temporarily forget about motivations from geometry and physics, and try to think of quantization the way an algebraist could possibly consider it. From that viewpoint, first of all, I will explain that quantizing Poisson algebras into associative algebras, it's natural and also in some precise way the only thing that you can do. So somehow, which is from algebra point of view, I think interesting itself. And then I will discuss a similar question in the non-associative context. So what do I mean by that? In some recent works in mathematical physics of the past 10, 15 years, there have been situations where you have a manifold and a bivector field, which is not necessarily by a Poisson bivector. So in general, so perhaps let me say that. So suppose that M is a manifold, and around the bivector field, and then you can define a bracket on functions by saying that the bracket of f and g is equal to lambda applied to the paired with the gradients with the different differentials of these functions. So somehow, so this f and g were smooth functions on the manifold, then you get a smooth function out of that. And if lambda is a Poisson bivector, meaning that an operation called the house and 9 house bracket of lambda with itself is equal to 0. Then what you get is a Lie algebra. These brackets satisfy the Jacobi identity. Well, and in fact, it's an if and only if statement. So
F and G is from the C side. Yeah.
Right, but sometimes in some situations of interest to mathematical physics, apparently this bracket is considered even if lambda is not a Poisson vector. So there are numerous references that I can give you in the end of this talk. So sometimes this first situation for the Poisson vector, this is the context of classical mechanics, for example. But sometimes lambda is a more general vector. And you still want to know something. So what is it that something that you want to know? Sometimes you want to use the product of functions and this bracket to construct a certain operation called the star product. And when I say star product, for the purpose of this talk, I mean the following. So you define an operation so here f and g still belong to the to smooth functions on your manifold. You multiply the functions to begin with, then you add the deformation parameter h bar, or sometimes people write h bar over 2, so perhaps I will do just that, times the bracket, plus some other terms. So here h bar is a formal parameter. And your goal is to write a formula which will be somehow, in one way or the other, physically meaningful or geometrically meaningful. And that, of course, leaves some room for interpretation. So classically, for quantization in the classical sense, we want this star product to be associative. And somehow this was the question of existence of such formula was posed in late 70s by Flato and his collaborators, and was, of course, for smooth manifolds famously resolved by Maxim Kontsevich in his work on deformation quantization, which is in many ways a beautiful, tremendous accomplishment. Again, outside this classical situation, when your bivector is not a Poisson bivector, you have no hope for this to be associative, because, so let me perhaps see that. Let me write here that f star g minus G star H. So the product of functions is commutative, so it goes away. G star F, thank you, is equal, so H over 2, the bracket is antisymmetric, so it's loaded 2 times, so it's H times the bracket, plus something, little o of H. Plus something much smaller. For the associative product, the operation AB minus BA does satisfy the Jacobi identity, and which forces, which means that this bracket also had to satisfy the Jacobi identity to begin with. So wanting the product to be associative is only possible if you start with a bracket that satisfies the Jacobi identity. Now, so you might want to ask, so okay, suppose that this bivector does not quite satisfy the Jacobi identity. That is, you consider something weaker. So, for example, no identities at all. So it's just a sufficiently general anti-commutative operation of functions. So, what could you expect then? Or can you? So, of course, you can say maybe if the bracket didn't satisfy any identities, maybe this star product also doesn't satisfy any identities, and that's fine. But this way, this is a little bit too extreme, because you are deforming a commutative associative product. So you kind of expect that there are some remnants of that that will still remain. Then somehow you look at physics papers where they actually consider some situations of interest for non-Poisson bijectors, and you find some very interesting things that they, for example, well, those physicists, yeah, so they want to understand, so what kind of algebraic structures one can hope for. Okay, you see that it's the star product is non-associative, so just how non-associative it is. Okay, it's natural to look at what kind of non-associative algebras algebraists study. Algebras which are associative but sufficiently close to associative. One famous example is the alternative algebras. Alternative algebras are algebras for which, if you write the associator AB times C minus A times BC, it's no longer zero, but it's completely antisymmetric in its argument. And somehow there is one paper of which I was recently reading, where it is established that non-associative star products usually are not alternative. So it's somehow alternativity is too strong as a condition. So usually, so non-associative,
you cannot choose bivector in such a way that it becomes...
No. That if you have various bivectors of interest and try to deform in the direction of that bivector, you get star products which are never alternative.
Nice. But is it possible to describe bivectors which will produce alternative formulas?
Well, that's a great question, which I don't know. I don't know. Well, yeah. Well, I suspect that it's good question. I'm not an.
Okay.
Well, yeah. So okay, let me actually say a few words about that question. So let me say a few words about that question. Well. Perhaps before I say that, I will also mention one kind of positive result that it was observed again by some physicists that all known quantization formulas for non-associative star products give algebras which are flexible. So that's another weakening of associativity. So known non-associative products are flexible, meaning that the associator is antisymmetric in the first and third arguments. E, B, A. So here, by the associator, I will always mean A star B star C minus A star C. So there is some kind of property close to, a little bit close to associativity, but not enough, not close enough. Now, so what the algebraic context that I'm going to discuss today concerns concerns a situation when I'm going take an absolute, so by vector of general position, so not satisfying any particular property. So which would mean that the bracket, which is anti-commutative, doesn't satisfy any further properties except for being anti-commutative. So context, algebraic context for today. The bracket is anti-commutative, but does not satisfy other algebraic identities. With itself, but of course, since we started with a bivector, there will be still the derivation property. So if you compute the bracket of f with the product of two functions g and h, it's fgh plus fhg. This is definitely still satisfying. And so things like that, algebras with two operations, one of which is a commutative associative product, and another is an skew-symmetric bracket which satisfies the derivation rule, have been studied in the literature to some extent. So they were introduced all more independently at more or less the same time in the geometric context. So there is I need to look at the reference. Yes, so there is a paper of, well, a memoir of Camas da Silva and Weinstein. From 99, and which somehow, so of course, yes, when you see the name of Albert Weinstein, you expect that it comes from the context of symplectic and Poisson, from a very geometric context in any case. So they introduced the term, they introduced the terminology almost Poisson algebras for these things. And by Ivan Shestakov in the year 2000, somehow, so who had this kind of idea that you are looking at a bivector in the general position, and well, he chose a terminology which is a little bit misleading. So in his original paper, those are called general Poisson algebras, which when you look at it in the first place, it makes you think that it's some sufficiently general but still Poisson algebras. So it's and then later in some papers with his collaborators, this was renamed generic Poisson, which doesn't quite help. So I mean, a couple of months ago, I was discussing it with Shestakov, and somehow we agreed that sort of almost Poisson is a more clear terminology. So yes.
Oh, there is another actual notion. I think when you look at the moment map, right? Not with values in the Lie algebra, but
Yes.
on the Lie group.
Yes.
There is something which is called quasi.
Yes, right.
Is it fitting to this picture or not?
So I think that I'm not so I'm pretty well. I'm reasonably convinced that it could be a particular case of this, but let me not be let me not say 100% sure. So in any case, so I think that. I think that almost Poisson, it kind of conveys some important intuition about it, because quasi it can mean almost anything as a qualifier. So throughout this talk, I'm definitely going to use this terminology, almost Poisson, for this algebraic section. Right. And so one reason I'm mentioning that is that then somehow Shestakov, he was also discussing some situation in that and other papers was discussing situations where about what you can say if you impose some identities on the bracket, and then you have the derivation property, and then somehow so for example, he introduced the notion of Poisson-Maltsev algebras, where somehow the bracket satisfies the Maltsev identity, which is somehow some relaxed version of the Lie identity, which was discovered by Maltsev in the context of understanding structures that you have on tangent spaces or two Mufang loops, and so you can introduce some other things. But let me tell you one thing which is very special about Poisson and almost Poisson. Something that makes it completely different from situations when the bivector satisfies some identities. So, it is of course well known that if you consider Poisson algebras, meaning that you have the commutative associative product, the bracket, and they are related by this derivation rule. Then the free Poisson algebra on some generators, some set of generators X. It's the same as the symmetric algebra on the free Lie algebra generated by X. So of course, using the derivation rule, you can rewrite everything as products of brackets, but it's not a priori clear that those form a basis, that those are linearly independent. And for Poisson algebras, it is well known. And similarly, there is a similar result here. So free almost Poisson algebra generated by X. It's the polynomial algebra on following Konstantin and Weinstein. I will call that other thing almost Lie. So free almost Lie on X. So somehow you don't, there are no dependencies between elements like that. By contrast, if you take some other identities, for the bracket, there always will be linear dependencies. So somehow there will be a surjection from the polynomial algebra on the corresponding free algebra, but it won't be an isomorphism. So this does not hold if the bracket satisfies some algebraic identities. And this is a result of Stakov and Stanley and some others from 2012, I think. So somehow, yeah. So it's so in this way, almost Poisson algebras are somehow perhaps intuitively the only literal algebraic counterpart of Poisson algebras, because this property of free algebras is certainly something that makes this type of algebras quite special in comparison with the others. Okay, now what I'm going to
you're not going to say what almost Poisson or almost free means, right?
Well, almost Poisson is this. It's
exactly this.
Commutative associative product, bracket without anti-commutative bracket, derivation rule. Yeah. And almostly anti-commutative bracket specifying no identity. Just one operation. Yes, yes. Yes. So I mean, of course, in the algebraic context, yes, it's just called the corresponding variety of algebras, variety of all anti-commutative algebras, or people who do sometimes would call it anti-commutative magmatic algebras or something like that. But yeah, so just yeah, whatever you call it, this is the statement. Hopefully, is clear. All right, and now. Let me so now let me recall one very elegant observation which originally goes back to unpublished work of Muriel Livernay and Jean-Louis Ladet from late 1990s. So, well, I think around 98. Well, I mean, actually, I mean, honestly, I mean, I cannot date it precisely because, I mean, there used to be some unpublished manuscript that several people saw. I've never seen the manuscript itself. I heard from other people what was written in that manuscript. So it's another. So it's they somehow observed, well, or rediscovered something that to some extent was, of course, known to experts in non-associative algebras, that there is an interesting, unusual way to think about all associative algebras. So consider for an associative algebra A, the operations so A, I will say, so I will denote product, I will denote by star the associative product, and I will consider the symmetrized product 1/2 of A star B plus B star A, and the bracket 1/2 of A star B minus B star. Then these operations satisfy the following identities. First of all, as I already mentioned before, in every associative algebra, the commutator gives you Lie algebras, despite the Jacobi identity. then turns out that the bracket with the symmetrized product satisfies the derivation rule. And the symmetrized product is generally non-associative, and it satisfies, but its non-associativity is equal to this iterated bracket. Which is kind of interesting, because this really so these axioms together, they are very close to the axioms of a Poisson algebra, right? So you have a commutative product and anti-commutative bracket, and they satisfy the Jacobi, the derivation rule, and this, which is the only thing which have to change, right? Because for the Poisson, this difference would be equal to 0, and for associative, it's this double commutator. Great. So now comes the suggestion, which I think that this suggestion may have.
Yeah. You have a structure like this, right? With
yes.
Product like this, and it's possible to go back to the source.
Yes, of course. So in fact, these identities.
You just add them, right?
These identities are equivalent
To the social.
to the associativity for the product A star B equal to AB plus the bracket. And yes. Right. So now there is an observation which again, I think was already made by Leone and Lode, but in any case was publicized by Martin Markle and Elizabeth Rem in early 2000s. So somehow now replace the last axiom by ABC minus ABC is equal to H bar EAC. So, you know, for H bar equal to 0, you get the Poisson. For H bar equal to 1, you get something which is equivalent to associative. And then somehow you might want to ask, what happens in between, right?
Probably something isomorphic to H equals to 1, no?
Yes. So well, yes, that's right. So if the ground field, which I'm always assuming, I didn't say that and I won't perhaps write it, I am always assuming the ground field to have characteristic 0, which was kind of hinted, for example, by writing 1/2 over there. But if the ground field is quadratically closed, if you can compute square root of any number, and H bar actually is an element of the ground field, because previously I was saying that I thought of H bar as a formal parameter. So now for a brief moment I'm thinking of H bar as an element of the ground field. So then these identities are equivalent to associativity of the product AB plus root of H AB. Because, well, this is a trivial observation, right? Because in all terms, in the first identity, the bracket appears twice. In all terms, in the second identity, the bracket appears once. So if you rescale the bracket, nothing happens to the first and to the second identity. But this identity is kind of inhomogeneous in terms of the bracket. And so if you just multiply the bracket by root of H, you are reduced to the case H equal to 1. So this is a rather trivial observation. And then somehow, this already is explained in the paper of Marco and Ram from, I think, 2003, if I remember correctly. And then they explained also that, however, that if you think of H bar as a formal parameter, you can somehow restate algebraically what deformation quantization is.
Just one question. You see, in the case of associative algebra,
yes.
Right. So, what will be in this language, now we have two operations, right?
Yes, so this somehow, but this will, well, since we already see that these identities are equivalent to the identity of associativity, this will give you a homology theory which is equivalent to so it's a different.
Which involves both operations.
That's right, but it will be some kind of, if you want, it will be the same Hochschild complex, but it will be you will write you will choose to choose some kind of different basis.
It doesn't like simplify.
No. As far as Hochschild homology is concerned, it complicates things. It doesn't simplify things, but it makes it possible to somehow state the question of deformation quantization.
Yeah, that's what I'm actually doing right now.
Yes. So somehow, using these identities, one can state the deformation quantization problem for Poisson algebras as follows. State of the, yes. Again, for this I'll need to put my notes. Right. So let A be a Poisson algebra. So then somehow a star product on A is okay. So let me perhaps introduce some notation. So I will. So if I have two operations, commutative product and anti-commutative bracket, that satisfy the Jacobi identity, the derivation rule, and this axiom. I will call them, for the time being, LLH algebras, where LL stands for Lerner and Lodé. So somehow now the axioms depend on the parameter H.
But you're not now assuming that you're working over the characteristic zero, right?
I am assuming characteristic zero is always assumed. And yeah, so just these axioms. So somehow so a star product of A is equivalent. So let me see. The datum of a star product on A is equivalent to the datum of LLH square algebra on H with coefficients in power series, where I assume that the all operations are now linear over the ring of power series. You can take H bar out by linearity. So such that if let me see what I want to say. Such that the the commutative operation is congruent to the product of A modular H bar and the anti-commutative operation is congruent to H bar over 2 times the Poisson bracket modular H bar squared. So remember, in the beginning, when we were writing the formula for the star product, we were writing, so it's the product plus H bar times bracket plus something else. And what I'm saying is that somehow all that something else you can distribute between the product, between the commutative and the anti-commutative part, so that the commutative part gives you, and the anti-commutative part now give you a structure of LL H bar algebra. Because, you know, in the deformation quantization, we were just saying that it is possible to extend. And now I'm saying that things which it is possible to extend to, they somehow can be grouped together with the commutative associative product and the Poisson bracket, giving you just two operations which satisfy precisely these axioms. So that's the observation that Martel and Wren made back in 2003. Now, okay, time flies really fast, but it's okay. In any case, I'm very close to, because this was all an extended reminder, almost. But now I'm ready to actually say something new. What happens here is that, so I think that what I find most amazing about these deformation formulas is that incorporating this deformation parameter H bar gives you a flat deformation. So this is easiest to say in terms of operad theory. I'm not going to tell you a lot about operads, but roughly speaking, when you in the algebraic context, when you say operad controlling some type of algebras, what it usually means is that for each n, you consider the vector space of all operations with n arguments linear in each argument that you can define in this context. So, for example, for associative algebras, it will be the vector space of dimension n factorial of all possible permutations, because you have the associative product, so the only freedom that you have is permuting things. Or if you take the Lie algebras, you will have the space of all multilinear Lie polynomials with n arguments, which is known to have dimension n minus 1 factorial, sorry, and it has some remarkable properties. And then you assemble all these spaces together and consider them together with the very important structure. You can substitute multilinear maps into one another, forming multilinear maps with more arguments. And that structure turns out to be of utmost importance for and helps to prove a lot of things. So what happens is that when you introduce this deformation parameter for each value of parameter, you get the vector space of multilinear operations you can define has the same size n factorial. Because, well, it's equivalent to associativity, so nothing really changes. And well, in the Poisson case, it also has dimension factorial that is known, let's say. Usually, if you have some identities and you introduce some parameter, usually when you specialize when your value of parameter is generic, the vector space becomes smaller because there are you obtain some non-trivial linear dependencies between multilinear operations. And here it doesn't happen. Here this deformation is flat. And this is a very remarkable, I don't know, I don't want, maybe saying coincidence will kind of diminish a miracle, let's say. Yes, not coincidence, a miracle, rather. And now let me state a new result, the first new result. So suppose that we take the axioms for Poisson algebras, and we want to deform them in such a way that we obtain a flat deformation. So we introduce some deformation parameter, and we want to obtain a new algebraic structure for which the dimension of the space of multilinear operations doesn't change. Then essentially the statement is that this is the only thing that you can do. So somehow the only flat deformation of the Poisson algebra axioms is given by LL-H bar algebras. And this, so okay, I can tell you that this result is combined out of two ingredients. So this is a new result. So and it is made up of two ingredients. One ingredient you can somehow only start with considering filtered deformations. So deformations of the kind that I was saying before, that you take the commutative product, then you kind of deform it with H bar times Poisson bracket plus something else. So somehow, and you assume first that the deformation somehow is filtered with respect to the bracket, that further and further terms use more and more Poisson brackets to define the things, how it happens in concentric formulas with quantization, for instance. And then you can classify, you can say that LLH is the only possibility in this class. And this is something that was done in my work with Murray Grabner a couple of years ago.
When you say flat, what means that absurd proportion will become zero, right?
No, well, when I mean flat, I just mean that these axioms, it's an operad now over the ring of polynomials in H bar, right? And I want the space of multilinear operations to be a free K H bar module of rank n factorial. So flat deformation in that sense.
I see.
Yes. So first, the strategy of the proof. First, classify filters flat deformations in a certain sense. And this is so my work with Nuri Bremner from 2020, I suppose. And then prove that all deformations actually are filtered. And this is a very recent result. So I mean, it's part of a paper which will appear on the archive in a couple of weeks, probably. Right. So now I have a few minutes. Let me just say what happens in the almost Poisson case. So, what about almost deformations? The situation turns out to be surprisingly different. In a sense, that depends how you look at it. Some people might say simpler. Some people might say more disappointing in some way because it's too simple. So somehow they the statement in the case of almost Poisson is as follows: that if you have a flat deformation of almost Poisson axioms, then the corresponding algebraic structure is just equivalent to almost Poisson. You cannot go outside. So from Poisson, you can kind of run away and go in the associative world. From almost Poisson, you don't really can run away that far. So I'll explain precisely what this means. So flat deformation of the axioms of an almost Poisson algebra gives an algebra gives axioms gives algebras equivalent to almost Poisson. So to make it precise, and let me write the corresponding axioms. So the corresponding algebraic structure appeared in several different papers. So historically, it first appeared in work of I think he was, I'm not sure, there's American or Canadian copyist from 1960, I suppose, yes. And so somehow Shestakov, who used these algebras in one of his papers, proposed to call them Cocoris algebras, and they satisfy the following identity. So you consider algebras with one operation star, So A star B, and the following axioms. So let me write the axiom in the following way. J, A1, A2, A3 is equal to 4 times the associator minus A1, A3, A2. So here, here the bracket AB is A star B minus B star A, the commutator. This is the associator. And J, well, it's the Jacobiator, so it's the left-hand side of the Jacobi identity for the bracket. ABC is equal to AB. Let's see, yes, ABC plus BCA plus CA. So just this one axiom. And so somehow this result, the result that the flat deformation is equivalent to almost Poisson, says the following, that somehow if you have an almost Poisson algebra, then you can define a very stupid star product given by AB plus H bar over 2 AB, and you stop here. Just yeah, and the statement that the flat deformation uses says that this naive star product essentially satisfies the exact same axiom that most complicated star products would satisfy.
And how about in this case?
No. Here, in this case, of course, the product, the commutative product is non-associative, so you know it's here.
Higher.
Yeah.
Higher is defined by the same way as for quantization.
Well, it's fine if you want by quantization. Yeah. Well, so somehow, so in some sense, the upshot of this result says that the trivial for almost Poisson algebras, algebraically speaking, the trivial quantization is as good as it gets. So if you cannot find nicer formulas that would satisfy nicer identities or more interesting identities, the algebraic identities would be exactly the same. Now, let me remark one thing here. Look at this formula. So here, this term is antisymmetric in A1 and A3. The Jacobiator is fully antisymmetric in its arguments, which implies that the associator is antisymmetric in A1 and A3, so we recover the fact that deformation quantization of almost Poisson algebras is always flexible. So the associator is antisymmetric in the first and third argument. So something that was observed in physics literature. And of course, it is an easy computation that shows that this axiom of covariance algebras is not strong enough to ensure alternativity. So we also get a rigorous mathematical proof of the observation that non-associative star products are not alternatives. Another thing that was kind of observed in some particular example by physicists.
This star product actually is due to covariance, right?
Well, yes. So essentially, yes. So covariance, he was studying something that he was called model non-commutative Jordan algebra. So he was motivated by some entirely different things. And somehow, yes. So and then, yes. So his examples were obtained using by vector, using a bracket that by vector with polynomial coefficients induced on the ring of polynomials in several variables. So he definitely was considering that exact thing. He just didn't care about this particular bit of the picture, which came into focus much later. Right. So perhaps it is prudent to wrap it all up. So again, this result. So this result, it's proved in a very similar way. So somehow by certain representation theoretic argument, you explain that every deformation happens to be filtered, and then classify filtered deformation by rather direct computations and computation. It's not a difficult result. I think that this result is interesting for. This viewpoint is perhaps interesting for two reasons. First of all, it tells us that a lot of things that happen that naturally arise in questions of quantizations in mathematical physics, a lot of properties can be somehow guessed and recovered by a purely algebraic viewpoint. So somehow this result essentially shows that the only non-trivial thing into which you can hope to deform Poisson algebras are associative algebras, which is kind of course, what physicists always know for those known, but this way, yes, and here.
For example, any Poisson structure is almost Poisson.
Yes.
So in the category of almost Poisson structures, this is the. So in particular, when you take a symplectic structure, right?
Yes.
A symplectic chain structure will give you a while algebra, right? The first while algebra.
Yes. Of course, and this property relaxes associativity. So somehow, yes, of course. Well, no, yeah, this property relaxes associativity.
By the way, did he also prove that the only flat deformation of this one is this one? He didn't mention about.
No. I mean, this is not. So no. Again, okay. There is a very important distinction here,
right?
Because there are two types of deformations happening. For each individual algebra, you can talk about its flat deformation.
Right.
This is where deformation quantization happens. And now I am talking about flat deformation of operads controlling these algebras. So of course you have this question about the flat deformation of the operad of Poisson algebras, and there you find associative algebras as what you should deform it into. And if you look at all almost Poisson algebras, for the corresponding operad, there are no non-trivial flat deformations. So you can write the trivial deformation into covariance algebras, but it's equivalent algebraic axioms. So that's the upshot, the complete upshot of this viewpoint. Right. So I think that it's now I can definitely stop, and thank you for your patience.
Thank you very much, Olga. Any questions or comments?
Yeah, maybe I can ask one question. Yeah, so
Yes.
what would be the next sort of any sort of?
Well, okay, so there is.
For example, you see what I mean, like in terms of like Lie algebras, like this.
So I can tell you what is one very natural related question. So there is. So in a few years ago, in 2017, I suppose, I was very lucky to have made an observation which I like very much. It concerns the following thing. So there is one other way to. So I was now talking about Poisson algebras and almost Poisson algebras, and somehow there is this kind of way of relaxing the axioms of Poisson algebras. There is another way which kind of relaxes things in a different direction. There is something which ultimately I call F-manifold algebras because, well, it contains it geometrically. It relates to something that Hertling and Manin introduced and called F-manifolds in the geometric context. So there you have an associative commutative product, a bracket that satisfies the Jacobi identity, but the derivation rule is relaxed. You no longer have the derivation property, but you have the axiom that writes the bracket of two products as something. So you cannot eliminate everything, but you can just do that. So they found the structure somehow in the context of studying some particular type of Frobenius manifolds arising in singularity theory and so on. And so somehow I was lucky to have observed that these F-manifold, so Poisson algebras are, physicists would say, quasi-classical limits of associative algebras. And in the same sense, F-manifold algebras are quasi-classical limits of the so-called Prelli algebras. So for F-manifold algebras, you have to replace associativity by Prelli, meaning that the associator is symmetric in the last in B and C. So this is the algebraic axiom. And then later, there is a paper of Chineva and his collaborators discussing deformation quantization problem in this context. So somehow, I think that it would be interesting. It would be interesting to take the operad of F-manifold algebras and classify all flat deformations of it to see if this somehow singles out Prelli in the same way as in my example now associative the associative axiom is singled out by the flat deformation condition. So I think that this is one natural direction. Another natural direction is, of course, to try to find out any other situations where you have somehow this flat deformation of a certain kind. There aren't that many examples, to be honest, and I suspect that finding any new examples of that kind actually will teach us something interesting, something new. So it's a very open-ended question where there is a potential to find many interesting things.
Thank you. More questions or comments, please?
Yes. So you said before that the free
Almost
Poisson algebra is the symmetry.
Yes.
So in the case of Poisson and Lie, this gives you this in the end kind of inducing this PDW property, right?
Yes.
Does it induce some PDW properties like?
Yes, good question. Good question. So I would be inclined to say that in this case the corresponding PBW theorem is trivial because you are not leaving this variety of algebras. You just kind of do some change of variables. So yes, I mean in principle yes. So if you if you want, I don't know, if you want to impress someone without saying anything meaningful, you can say that yes, that the free Kokoris algebra is isomorphic to the underlying vector space is the space of vector space of polynomials in but I mean it's a trivial result because you just do some change of variables. You don't consider two different varieties of algebras, and they are equivalent in some precise way.
Right.
Thank you. More questions? So if there is no question, let's thank Professor Dotsenko once more. Thank you very much.
Thank you.